All right, folks, so I think it's about time to get started again. All right, so hopefully you can all hear me. I'm slowly losing my voice throughout the course of this conference, so it'll be fun to teach a course starting next week at MIT. But in any event, today we've got one more topic in our sort of grab bag of interesting places where geometry appears in machine learning to cover for our summer school today, kind of continuing the theme of places where you might not think of geometry appearing in the machine learning world, right? So, of course, there are many cases where it's very obvious that you need to think about geometry, you know, like actually machine learning from a shape or a graph, like what Michael talked about. But there are also many geometric methods in machine learning, and today we'll cover a third sort of set of these things. And in particular, today's talk is almost going to be a little bit closer to the computer graphics world because that's the world that I'm a little more comfortable in. But then at the end, we're going to link what we talk about back to some more abstract techniques that maybe we no longer can have the nice renderings that we'll see in many of the slides at the beginning of our talk. But exactly the same techniques carry over to the high-dimensional regime with almost no change. And so I've attempted, it's a little bit of an experiment, we'll see if it works, and it links to, I think, some stuff Michael has already covered. But essentially, there's a very particular technique in the geometry world that's very common in theory, which is to use operators like the Laplacian, which we'll define, not to worry, as sort of a means of sensing information about a shape. So this is, you know, the Laplacian is roughly like the thing that takes a function to its second derivative. Right? So it's an operator, it takes functions in and outputs other functions. And we'll see that by looking at things like the eigenvalues and eigenfunctions of this operator, we can learn quite a bit about a shape. And this is useful for a lot of tasks, both in the low-dimensional regime, where it turns out that Laplacian eigenvalues and structure are useful for tasks like shape retrieval and 3D recognition and things like that. But then also, exactly the same operator appears in semi-supervised learning and the sort of high-dimensional regime where, again, the sort of big theme of many of the techniques that we've spoken about in the last couple of days is how do you have these techniques that can sense the geometry of your data cutting out a very small piece of a high-dimensional space. Right? And so we're going to continue that theme, but every single time that we've talked about it this week, it's using a completely different approach, and today will be no exception. Okay, so that's our basic setup. Just like yesterday, it's actually the same URL. I added the slides for today's talk here. It sounds like the slides for all of the talks at the Machine Learning Summer School will be posted on some Git repo or another, so I guess you'll get access to that as well. But for now, you can find it there. So that's tinyurl.com/solomon-mlss-2019. By the way, can you see the slides for today in there? I put them in, but I don't know if Dropbox worked. Okay, good. All right, the other warning that I should give you at the beginning of today's talk, there's a problem, which is that people in geometry processing, people in machine learning, and people in physics, and people in mathematics cannot agree on the sign of the Laplace operator. It's really irritating. In fact, I can give you some examples of research papers in my own discipline where about halfway through the paper, the sign of the Laplacian changes. My advice is that if you write code using these sort of techniques, if it doesn't work, try putting a minus sign in front of your matrix, and then maybe it will. I've made an attempt to go through these research papers and make them self-consistent. I think my Laplace operator is going to be positive definite rather than negative definite. I think physicists don't like that, but that's their problem. But there's a high likelihood of a mistake. So if you catch one, you're welcome to, come on stage and fix it for me. Okay. So the techniques that we'll be talking about today, just like last time, are this sort of, we're going to go back to our favorite data set here. I think I've managed to choose a slightly different rendering of it each time. And again, the sort of schematic that appears in this manifold learning world is that oftentimes your data, in this case, a point cloud in 3D, cuts out a piece of space that's much smaller than the full three-dimensional world. Like, so in this case, our Swiss roll example here is somehow intrinsically a two-dimensional shape. And hopefully at this point, given our series of lectures here, you guys kind of have some feel for what that means. But of course, there are a lot of challenges using techniques like this in practice, right? In particular, okay, if I give you the Swiss roll data set, for one thing, it's in 3D, so you can just look at it. But more typically, when you use these manifold learning techniques, or these crazy parameters like the dimensionality of your data, like the intrinsic dimensionality of your data, you know, like for instance, here it would be 2. And I think it's not so easy to sense that in practice, right? Do I have a 200-dimensional manifold sitting in, you know, 800-dimensional space? I would struggle to have a sort of reliable technique for detecting that sort of structure, right? And this is a pretty common area. By the way, for fun, I managed to find one example where that's not the case. So there's a colleague, we have it at Princeton. Let me see if I can load up a YouTube video on my laptop. Is this going to work? No. Ah, too bad. Oh, there it is. So my friend Roy wanted to find one data set where we actually know the dimensionality ahead of time. And he cooked up this really funny example where he took toy animals and put them on turntables and filmed it. So the data points here are actually in very high dimensional space. It's the frames of the video, right? So it's in like, you know, 100 by 100 space. But the dimensionality of this data is roughly 2, right? Because there's 2 rotating objects moving independently. So anyway, Roy managed to find a 2-dimensional data set. And indeed, these methods tend to be extremely successful on this species of data. But unless you're so lucky as to have Yoda and a toy dog on a turntable, I think that's a pretty rare scenario to be in. Maybe at home you have this sort of thing. But of course, there are many challenges in manifold learning that actually these tools are intended to address, right? So sort of a success of this machinery is that maybe you have 2 you know, things that are intertwined, and of course having a linear separator between your 2 classes isn't terribly successful. I think this is also a reason for kernelization. But even there, you know, when you map your data into a funny space, even if my data is 2-dimensional, something that people in computer graphics have known forever is that even if you have a 2-dimensional shape, it might be that the 2-dimensional embedding algorithms that we talked about on Monday are actually irrelevant, right? So for instance, here are 2 2-dimensional surfaces, and in order to map them into the plane, I have to introduce cuts and all kinds of crazy things to make that happen. So anyway, these are mostly just sort of geometric pictures to show you why in the machine learning world, or like here the presence of noise is obscuring the 1-dimensional structure, why these problems are so challenging. So today we're going to talk about some techniques where I want to perform machine learning directly on data that's shaped like a manifold, but I'd like to have techniques that also are somewhat insensitive to noise. And when I say noise, I mean the fact that my data is not a perfect sampling of the manifold. There may be holes, there might be slight perturbation, and so on, that's getting in the way of developing a perfect picture of our low-dimensional universe. Right? That the analogy we talked about yesterday in manifold valued learning of being a ladybug, I was thinking anteater, a ladybug crawling along a leaf that might be curved is no longer the right analogy because our data is so noisy that we don't even know everything about the manifold that we're working with. Okay? And there's many motivations for this, right? I mean, there's many worlds where, you know, you want to diffuse information around and the structure of your data is just a curved object that you have inexact access to. So the particular machinery that we'll talk about today is built in the language of partial differential equations, everybody's favorite area of math, I know. And essentially we're going to use terms like diffusion and spectrum, eigenvalues, and these sorts of things, but we're going to apply them in a machine learning context. And so the nice thing is that these tools will work equally well for doing things like recognizing bunnies, as well as, you know, other tasks like diffusing information around on maybe a road network or something like that, or even on a sort of high-dimensional space. Okay, so that's our high-level setup. So before we get to the machine learning point, I thought I'd give a bit of a historical perspective on where these kinds of problems came from, partially because I think they're easier to think about than some of the abstract techniques that we'll talk about later. So one of the big inspirations for this sort of spectral approach to geometry dates back, I think, to, well, I actually don't remember the date. Michael, you would know, the 1960s or so? Yeah, 1960s, roughly. Although this idea has been around a long time. So we'll say the 1960s. There was a mathematician, Mark Catch, I think is how you pronounce it, I'm not sure, who asked a very famous mathematical question. And that question was, can you hear the shape of a drum? Incidentally, I'm not sure this parses in Russian. It actually doesn't parse perfectly in English either. But the basic idea here that he was asking was, let's say that I look away and I hit some piece of geometry. You know. So I don't get to see the shape, but I get to hear the sound that it makes. The question is, if I can observe the audio, right, I can hear the vibration frequencies that come off of that shape, can I identify the shape? Can I reconstruct the shape of a drum based on the sound that it makes? All right, I'm going to try again surveying you guys. Every time I've surveyed this room, I've totally failed, but I'm going to try again. How many of us think that you can hear the shape of a drum? It's not totally unreasonable, right? Like if I make a drum bigger, it makes a deeper sound, so there's obviously some relationship between geometry and sound, yeah? Mostly on my left. Huh, over here. Cool. How many of us vote no? Ah, so the 50-50 split, except over here. They're sitting next to Michael, so that makes sense. Yeah. So, right. So let's illustrate our experiment a little more. So here's a animal from the Muppets, and he hits the drum. You hear it, and the question is that possible? Initially, this seems a little bit crazy, right? I mean, if you think about audio, it's sort of a one-dimensional signal, right? I mean, there's frequency, and that's it. But here's an example where you can. So I play the cello. For some reason, I put a guitar in the slides, but that's okay. Actually, guitar is slightly easier because the string vibrates. The cello has this added complication of a bow. But in any event, what do I do on a guitar? I strum the strings. I hear an audio clip. And now I put my finger down on the string, and that's how I control the pitch. Yeah? So geometrically, what happens when I put my finger down on the string? Well, in effect, the length got shorter, right? Because my finger is preventing the vibrations from going all the way to the top of the instrument. Okay, so it turns out that there's if you've played a musical instrument, I think you know that there's a deterministic relationship between where you put your finger and the sound that the instrument makes. Otherwise, it would be very difficult to play the guitar. And so indeed, this is a case where you can hear the shape of a piece of geometry. Namely, if I hear somebody playing the guitar, at least one string of the guitar, you tell me which string, then you can tell me where my finger was on the guitar that made the pitch that I heard. Does that make sense? There's definitely a relationship between audio and geometry, or between vibration and geometry. Okay, so at least in one dimension, it turns out everything works out. There's order in the universe, and I can hear the shape of a guitar. That's not quite true. I can hear the shape of a guitar string. Unfortunately, in dimensions 2 and higher, that's not the case. So here's a little bit of a spoiler alert here. So the answer is no, but. So in other words, there do exist drums that are isospectral, is the term, meaning two drums that sound the same, but have different shapes. Here's an example. The examples are kind of disappointing, but it took people, I think, about 10, 20 years to find nice examples in 2 dimensions. But they're extremely rare. And in fact, provably extremely rare. And the spectrum, or the audio that you hear when you vibrate one of these objects, actually tells you quite a bit about a piece of geometry. Not 100%, you can't hear the shape of a drum, but a lot. And of course, this theory, although I'm illustrating it, and we'll be illustrating it a lot today on 2-dimensional manifolds, it turns out those are the easiest ones to draw on a projector screen, lifts to the high-dimensional case, and that's going to be useful for tasks. Essentially, these kinds of spectral techniques are going to be applied to embedding, semi-supervised learning, and many other cases, okay? And so this is an area of mathematics called spectral geometry, and the basic idea here is that you can learn quite a bit about a shape. And when I say shape, I don't necessarily mean just a 2-dimensional object. I mean some high-dimensional object as well, by hitting it lightly with a hammer and observing the sound that it makes. And then more broadly, and one thing what we'll do is we'll talk about what does it mean to compute vibration frequencies, and we'll see that there's a very particular operator that shows up, something called the Laplacian. Once we can approximate this thing, and it turns out we can in a pretty reliable way on data, on surfaces, and many other modalities in between, there are many different ways to use it. Not only identifying one data set from another, that would be the sort of spectral geometry problem maybe, but also using it for inference, diffusion of information along a manifold, and so on. That essentially there's going to be one matrix which is really intricately tied in with the geometry of an object, and that just by computing that matrix, there's a whole suite of different computational techniques that fall into place. Okay. Unfortunately, unlike many, well, I don't know, actually, machine learning mathematics is pretty complicated. This is yet another topic where just constructing the beast that we care about in spectral geometry requires quite a bit of mathematics, and not mathematics you tend to see in undergraduate unless you were a math major. I was, which was convenient. So we're going to first introduce the Laplace operator. We're going to build up from simple stuff into the more complicated domain. Then we'll spend some time actually talking about applications in low-dimensional settings, things like shape recognition and retrieval. And then we'll see that exactly the techniques that we were using in low dimensions apply for high-dimensional problems as well. So in other words, we've kind of built up a nice intuition by looking at it in the cases that we can see, and that intuition carries over to other cases. So if you've ever solved the wave equation, I think many people have seen the wave equation in one dimension in their undergraduate coursework. Maybe you've taken a physics class. You secretly were using a Laplace operator, you didn't know it at the time. So in general, the wave equation is this sort of classic hyperbolic partial differential equation. One of the fun things of working in this area is there's lots of meaty math terms you can use at a bar and impress your friends. But essentially, the wave equation here, if I have a spring, is trying to describe the motion of a wave that's propagating along a one-dimensional line. Right? So here, the U can either express the compression of a spring, if it's like the slinky that I'm illustrating on the screen here. Or I think the more common one would be the height of the guitar string. Turns out that the one of the height of the guitar string, I have some questions about. That's just a Taylor series approximation, and it makes me a little uncomfortable, but that's a story for another day. But in any event, if you observe a wave propagating along a domain, like a spring, then one thing that you can see is that the compression or the height of the wave moving along the string satisfies this equation here. This is known as the wave equation, right? So c is the speed at which the wave propagates. And then the subscript here denotes differentiation in time or space. Right? So the second derivative in time of your wave propagating is proportional to the second derivative in space. This is our first example of a Laplace operator. And essentially, the Laplace operator is the thing that's operating on the spatial part of our wave equation. Right? So in particular, let's introduce some more complicated notation to get you guys confused. If I have a guitar string, remember the guitar string is sort of pinned at two sides, right? It's held against the instrument. So in other words, if L is the length of the string, then maybe we think of, at position 0 in L, the height is 0. Right? These are called Dirichlet boundary condition. Then the wave equation is that the second derivative of u is equal to, the second derivative of u plus the Laplacian applied to u is equal to 0. It's going to be my first sign mistake today. Yeah? Where the Laplacian is this funny operator that takes a function u and maps it to minus its second derivative. We use the word operator a lot today. We also saw it yesterday. So an operator is a thing that inputs a function and outputs a function. If you're not used to thinking about this kind of thing, think about a matrix. Right? So if I took u and I discretized it as just one value per point on a line, right, then this thing is nothing more than just like applying a matrix to that vector of height values. And really that analogy carries through. Like, for instance, if I take the second derivative of the sum of two functions, that's, of course, the same as the sum of the second derivatives of those two functions. And similarly with scaling. So this second derivative operator is just like a matrix, right? It's a linear thing. Okay. So what do we do to matrices? Well, two things. One is we invert them. The other thing is we compute their eigenvalues. Anybody know what the eigenvalues of this operator are? I'll give you a hint. What's the second derivative of cosine? Who said cosine? That's not true. It's minus cosine. Yeah, so, and similarly, the second derivative of cosine of ax is a squared minus a squared cosine of ax. Yeah? What does that mean? I put in a function into my operator, the thing that computes second derivatives, and what did I get back out? I got a scale of that function. This is like an eigenfunction of the Laplacian operator. Right? So exactly the same linear algebra carries through. And in fact, if you look at the eigenfunctions of this operator here, subject to these boundary conditions that my string is fixed at positions 0 and L, then what I get are eigenvalues that are equal to pi k over L. And mathematically, what does that tell us? That tells us that I can hear the shape of a string. Right? Because take a look. The eigenvalues, those are the frequencies that I hear when I vibrate the string, have L hiding inside of the expression there. So if I want the length of the string, I could just read it off of this formula. Okay, so everything carries through. So the one-dimensional picture is nice. There's order in the universe and things work well. Now let's kick it up a notch and talk about regions in Euclidean space. So now this is like a drum, but the drum is flat. It's not curved yet. So in particular, let's say that I have a region omega in R2. So R2 is the plane. I can still write down the same Dirichlet eigenvalue problem, right? The same thing that's asking me for vibration frequencies of my drum, subject to the condition that on the side of the drum, the elastic material is pinned down, it can't move. And now the operator, if you've taken a physics class, you've probably seen this, takes the second derivatives of my drum and sums them together. And that is going to be the operator that I call the Laplacian of this of functions on this shape. Does that make sense? So it's the thing that takes a function and maps it to a new function, which is the sum of its second derivatives. That's what we see here. We're going to use that delta sign for that. Incidentally, I think when you take a physics class, you're totally you agree with this formula, it seems cool. This should look really suspicious to you because it's written in coordinates, right? It's like the second derivative in x plus the second derivative in y. But physics doesn't know if I take my drum and rotate it 30 degrees. There's something a little bit suspicious about this formula, why are x and y so special? So one thing that you can check about this formula is that it's rotation invariant, but it's actually not obvious from the way that I've written it here. That better be true, right? Otherwise, I take my drum and I rotate it and it makes a different sound. It would be a pretty crazy drum. Okay. There's many different ways to notate this Laplace operator, right? Well, one thing that people do is write it as divergence of gradient. I think we all are very used to the gradient operator in machine learning. And the thing that we can check is that, in fact, although it's not obvious from that second derivative formula, the Laplacian operator is coordinate independent. Meaning if I take a domain, I rotate the domain, and I take a function on the domain, and I rotate it with it. If I apply the Laplacian to that function, and then I rotate it, that's the same as rotating the function and then applying the Laplacian, right? These two things commute. Okay. So there's many different places where the Laplacian appears. One is in the wave equation. Another one that's particularly important in machine learning is something called the Dirichlet energy of a function. So let's say that I have a function u on my weirdly shaped domain here. And I want to know how smooth u is. Right? Some functions are very smooth, some functions not so much. Okay, so a non-smooth function is maybe one that varies a lot, wildly oscillates between small and large values. And if I look at the gradient of that function, what is it going to look like? Well, if my function changes a lot, right, in very small amounts of space, it keeps oscillating, the gradient is going to be a very big vector, right? Whereas if I have a very smooth function, then the gradient is probably pretty small, right? It doesn't change all that much. Exactly the same intuition we use in machine learning all the time. So if I want to measure how smooth a function is, one way to do it is to take the gradient, right, that's what's hiding inside of this expression here, and take its norm as a vector, and then just integrate that over the domain. So first of all, when is this function 0? Or when is the Dirichlet energy 0, rather? Whenever u is a constant function, right? Because constant functions have no gradient. And somehow constant functions are also extremely smooth, right? So it all kind of works out. Yeah? So one thing that we can see if you integrate by parts is if you take this expression for the Dirichlet energy, you apply Green's theorem, you might remember that from your calculus class, then what you'll get is that this is actually equal to minus the integral of u times the Laplacian of u. So there's another place where that same Laplacian operator shows up again. And in fact, if I want to write down an optimization problem that says find me the smoothest function, in other words, minimize the Dirichlet energy, subject to boundary conditions, so like maybe I prescribe the color on the boundary of the domain and I just want a smooth function on the inside that interpolates it. One thing you can show is that that smooth function satisfies that the Laplacian of the function is equal to 0, identically. This is called Laplace's equation, and it's going to be extremely useful for semi-supervised learning. So in the semi-supervised learning world, right, maybe I have a lot of data points, and then a few of them have labels on them. And one thing I might want to do is propagate those labels in a smooth fashion to the rest of my data manifold, right? And that's exactly the sort of problem that we've written here. Okay, functions whose Laplacian is equal to 0 are called harmonic. They have many beautiful properties. We're not going to go into this because it's, well, it is relevant to machine learning, but maybe not directly. One nice one is something called the mean value property of a harmonic function, which says that the value of a harmonic function at a point is equal to the average of that harmonic function in a little neighborhood of that point. This is a little bit crazy, right? So like every point is equal to the average of its neighbors. Which sort of makes sense, right? For a smooth function, you really wouldn't expect there to be some local maximum, right? Because I could make it smoother by taking that local max and just pushing it down. Yeah. Okay. And there are many applications of harmonic functions, everything from machine learning, computer graphics, shape recognition. These things appear everywhere. One of my favorites, I used to work at an animation studio, and they actually, harmonic functions appear in how you deform animated characters. Right, because oftentimes what you'll do, an animated 3D model is composed of many millions of vertices. An artist can't really control that. So maybe I put some control points around the outside of the model, and then I compute the influence of the motion of those control points by solving a harmonic equation, which is pretty nice. So it's called harmonic coordinates. Okay, the Laplace operator, it turns out, we've already seen, I guess this morning you heard about kernels, so you almost inevitably, I hope, saw positive definite matrices. And the Laplace operator is somehow an infinite dimensional analog of a positive definite matrix. So remember, what does a positive definite matrix do? So if I have a positive definite matrix A, now I take any vector, and I do any non-zero vector, and I have x transpose times A times x, what do I get? I get a positive value. So similarly, if I take a function and I compute the integral of that function times the Laplacian of that function, so it's kind of like f transpose times Laplacian of f, I'm guaranteed to get a non-negative value. It's actually quite easy to prove, right? Because essentially you take that expression for Dirichlet energy that we had in the previous slide, you go backward, right? Because, let me load up that slide. The Dirichlet energy is very obviously positive, right? And the integral of f Laplacian of f is exactly the Dirichlet energy of f, so you get a non-negative value. These are some nice properties. And we'll see that this carries through, that when we discretize this object, we're going to get a positive definite matrix. Incidentally, one common misconception. Let's say that I have data at a few isolated points and I want to interpolate it to the rest of my manifold by solving Laplace's equation, right? That's what I just sort of proposed to you guys. Physically, the analogy here is kind of like a tent pole. So I have a big piece of elastic, and I kind of pin it up at certain points, and then I'm using the elastic to settle to interpolate the rest of the data. I just spent a lot of time talking about smoothness. Is this a smooth interpola? Almost. Except right at the places where I've prescribed information. And so that's actually going to be a little bit of a fishy aspect of some of the algorithms that are out there. They disregard this fact. They talk a lot about smoothness, but actually right at the places where I have information is where my interpolant is going to be smooth. You can fix this by using higher order operators, but it's a little bit tricky. Okay, so now let's talk about Laplace operators on graphs. So far we talked about smooth objects like things in Euclidean space. Now we're going to step sideways, talk about discrete domains. Again, my goal here is to define the same object on a lot of spaces so that you kind of have an intuition for what it's doing. Okay? So a graph is just a collection of vertices and edges. And when I talk about a function on a graph, I'm going to talk about it like an assignment of one value per vertex of the graph. Okay? So now this is a discrete object. It's like a vector in R to the number of vertices. So remember that the Dirichlet energy of a function was I took the gradient of the function, I squared it, and I integrated it. So let's say a function is now one value per vertex of a graph. What would be a reasonable notion of Dirichlet energy? I'll let you think about it for a second or two here. Well, we've used the vertices. We haven't used the edges yet. Yes? Yeah, exactly. So I could, on every single edge here, I could take the difference between the value on the two endpoints of the edge, subtract those two things, and square and sum that up. And that's some reasonable notion of Dirichlet energy, right? For one thing, it's 0 for constant functions, at least if my graph is connected, and kind of grows with the craziness with which my function changes from vertex to vertex on the graph. Yeah? And that's actually a totally reasonable analogy here. So let's notate that a little bit in linear algebra. So let's define an object called the edge incidence matrix. So this is an edges by vertices matrix. So in other words, it takes in as input one number per vertex and outputs one number per edge. And all it does is for every edge, outputs the difference between the value at one endpoint and the value at the other. We're going to arbitrarily orient every edge, by the way. It's not going to matter for our expression here. So the Dirichlet energy then, just like our colleague here has suggested, he's absolutely right, can be notated in two different ways. I think what we described is on the right-hand side, right? So for every edge, I subtract the two values and I square. I want to write that in nice, slick linear algebra notation. Then I get this expression here. Make sense? So what did I do to get from the gradient to the Laplacian operator? I kind of integrated by parts. And it turns out that that's a very simple thing to do when I'm in a graph. It's just linear algebra. Because of course, what is the norm of df? So in general, if I have a vector, x, and I want its norm squared, what do? I just compute x transpose times x. So what is the norm of df? Well, it's f transpose, d transpose, df. That makes sense? I would write it down, but I'm giving up on boards today. Okay, so remember, f transpose, d transpose, df. So what if I parenthesize that in a different way? So I have f transpose times d transpose, df. Remember we had two expressions for the Dirichlet energy, right? One of them was the integral of the gradient, and the other was the integral of u Laplacian u. So somehow, our Laplacian operator is exactly this matrix d transpose d. And that's something we can call L. And indeed, this thing is called the graph Laplacian. It appears all over the place in a very nice area of mathematics called spectral graph theory. It's a pretty common one to use. It's a symmetric and positive definite matrix, which is very easy to check from the expression here. And essentially, a lot of the properties that you can prove about the smooth Laplace operator carry through to this guy on a graph as well, with basically just a notational change, which is pretty nice. In fact, they tend to be easier to prove here because there's no integrals. So for example, we talked about the mean value property here. One thing to notice, if you write down the expression for the Laplace matrix, is this very simple. It just ends up being down the diagonal, the degree of a vertex, and then all the off-diagonal entries are just like the adjacency. So if Laplacian is equal to 0, in effect, if you just read off that relationship, what it's saying is that the value at a vertex is equal to the average of the values of its neighbors. So that mean value property carries through, which is pretty nice. And just like you can ask, can I hear the shape of a drum, you can actually ask, can I hear the shape of a graph? Right? So I compute this matrix, I take its eigenvalues, and the question is, does that list of eigenvalues tell me the topology of the graph, like the edges? Notice it's not the same quite problem that we've laid out so far. So we have one positive answer, which is for strings, which are one-dimensional, a negative answer, which for drums, which are two-dimensional, or n-dimensional. Somehow a graph is in between these two things. Just for fun, how many of us vote, like, can you hear the shape of a graph? I compute this matrix, I compute its eigenvalues, I can get its structure. Yeah, we're not going to walk into my trap anymore. Yeah, the answer is actually no. So here's two graphs. These are, I think, called enneahedra, and they're not the same topology, like you can't map them to each other, but they, if you you'll see, okay, you'll see that they're the same. If somebody's really bored and has MATLAB on their laptop, I encourage them to give this a try. They're not so big. If you like this kind of area, there's all kinds of beautiful math out there, and it's actually much more elegant than, well, elegant is the wrong word, much more digestible than the variational version of this story. There's a very famous textbook, which I'm showing you on the screen here. One of the really beautiful things is the graph Laplacian gives you sort of a connection between differential equations, like the Laplace operator, and discrete math, like what happens on graphs. And there's some really beautiful formulas that link these two things. So a very famous one is something called Caritas Theorem, which tells you you can actually compute the number of spanning trees in a graph, which is like somehow a very combinatorial type of computation by looking at the determinant of this matrix, which is surprising. In fact, actually, I was just applying this yesterday. So we're about to post a research paper in American political redistricting that uses this formula, which is kind of funny. Okay, and then finally, because we're talking about manifold learning today, we should talk about manifolds, of course. Everything we've talked about so far is either a graph or something flat, right? So remember yesterday we talked about scalar functions on a manifold like a surface is nothing more than an assignment of a real value to every point on our manifold. And we also defined the gradient operator yesterday. Remember we used it to talk about manifold value gradient descent. So we've already defined that. So we have all the ingredients we need to define a Laplace operator, which is why I was sneaky about starting with the wave equation, moving to Dirichlet energy, and then we're working with that, because the gradient operator is easy to define on a manifold. And so all you have to do if you want the Dirichlet energy of a function is take that gradient, square it, and integrate it. And indeed, here I have a bunch of functions on the Stanford bunny here, and they're organized by decreasing Dirichlet energy. We actually did compute it, so this is a true value. And you can see that as you move to the right, the function somehow becomes smoother. Yeah? Okay. We're going to skip today because we don't have so much time, this integration by parts argument. But essentially, hopefully I've convinced you that for every quadratic energy I can put on a function, there exists an operator so that this thing is, this relationship is true, right? That, you know, if I can integrate gradients, dot products with each other like that, then by just like the same way that I parenthesized, remember for the Laplace operator, I had that d transpose d and I just kind of parenthesized it the other way. So somehow I have something very similar here, right? Like I have the dot product between df and dg, and by parenthesizing it the other way, or applying Riesz representation theorem, depending on whether you like math or intuition, out pops an operator that's known as the Laplace-Beltrami operator. We throw on Beltrami because he was the first, well, I don't know about the first, but one of the first mathematicians to talk about Laplace operators on curved domains. We're going to see that, like if you Google for the formula for the Laplace operator on a manifold, it's kind of scary looking. But we'll see that actually the discrete versions are easier to think about. So we'll kind of jump to that and then work backward for this thing. Okay, and of course, one sanity check that you can check is if you have a function on a manifold and you take a local parameterization that looks like the exponential map, so locally it's kind of an isometry, then the Laplacian in the parameterization of your function is the same as the Laplacian of the thing in the curved object. And so, for instance, if you want to compute vibration modes of a domain, it's nothing more than you take that operator and then you compute its eigenfunctions, just like we already did for a string. In fact, that leads to a very famous experiment. I don't know if you guys have seen this before. It's called the Chladni plates. So you have a plate, and you play a tone next to it, right? And so the plate vibrates at its different vibration frequencies. And now I pour sand on top of the plate. Now, in general, the plate is vibrating up and down, right? So what happens to the sand? It just bounces off of the surface, except in certain places, which are called nodal domains, or the boundaries of the nodal domains, where the function is kind of vibrating about that point, right? Like so on cosine, right? Like right where cosine equals 0, there's actually no vibration, right? So let's see if we can play this clip. Hopefully the audio won't be too loud. In fact, there's no audio. Oh, that's okay. So imagine that you're hearing a pitch and it's getting higher. It's probably just as well that you can't because it's kind of irritating. And then what'll happen, maybe we'll fast forward a little bit. Notice the sand is starting to kind of bounce on the surface here. It's a little hard to see. So what's happening is they're playing a sound and they're increasing the pitch. And eventually, notice what happened. The sand traced out a circle. And that's because that corresponds to the first eigenfunction of this plate here. As they increase the pitch, the sand traces out the different eigenfunctions of the Laplace operator of this particular shape. So here's a circle. Later on, it's kind of hard to aim here. So there's like concentric circles and so on. It's kind of, this is every year when I teach my geometry course, I offer extra credit to a student who can reproduce this, and they never do because it's a lot of work. Incidentally, there's a nice application of this machinery, and if you have an instrument and you bring it to an old school repair shop, sometimes they'll put sand on it and hit the side because you want to put the sound post of your instrument in a place where it's not vibrating too much. Okay. In any event, now that we've computed the Laplace operator, of course, we should talk about how to use it. And there are many places this appears. So for instance, not just the wave equation. If you take that du dt squared and just get rid of the square, you get the heat equation, which sort of defines how temperature diffuses along a domain. So we've laid out the theory. Now we have to ask about, I have my data, cuts out some high-dimensional manifold. Can I approximate this operator in that regime? And of course, I wouldn't be here if the answer was no. So let's talk about how to do that. There are many different strategies for approximating Laplace operator. Some of them are morally justified, some of them a little bit less so. But it's important to be aware of many of these. One very simple thing that you can do is you take your data, you compute the k-nearest neighbor graph. Now that you have a graph, I already gave you a formula for the Laplace operator as a matrix of the graph. And it turns out that actually this is a pretty reasonable stand-in for the actual Laplacian of the data manifold. Right? So again, you compute connectivity, but just computing nearest neighbors, and that's what you use. Notice, for instance, if I diffuse information along this graph, that for instance, the yellow points will receive information from the black points much later than if I just used like the two-dimensional plane. Does that make sense? Cool. Right. It turns out that k-nearest neighbors graphs can be a little bit brittle, right? They're kind of making a binary decision as to whether to insert an edge or not. Probably the more famous technique for computing Laplace operators on point clouds goes to Misha Belkin and some of his collaborators in the early 2000s. And the nice thing is it just fits on a slide, and they can prove under certain sampling circumstances that if I sample my data very, very densely, this operator actually converges to the Laplacian operator of the underlying manifold. And notice this is a very simple formula. All it's saying is that I take a Gaussian in the distance between my data points, and I construct a matrix out of that, just pairwise between every pair of points. So this is just to convince you guys that actually approximating Laplace operators on your data manifold is not so complicated. It's actually fairly straightforward. There is a challenge here, which is, let's say that I have 10 billion data points. Can I compute this operator the way that I've defined it here? No, this is a billion by billion matrix, and every single entry is non-zero. Right? So that's not so great. So typically what people do is actually sort of a combination of the last two slides, right? Like maybe they compute the k-nearest neighbors, evaluate this formula just in those neighbors, and then just clamp the rest of the values at zero, and then that's a pretty reasonable thing to do. By the way, I use the word reasonable because I think it's very hard to prove theorems when you start to introduce those sorts of approximations, right? So the easier theorems are when you have this full matrix, and things get tricky when you start to introduce these approximations that make it easier to compute. And then finally, it's worth mentioning one very famous formula. Specifically, if you're in 2D, you care about like 3D shape retrieval, that kind of application. Then there's a very nice formula for Laplace operators on a triangulated mesh. If you go to a conference in geometry, processing, computer graphics, you'll see this formula all over the place. This is called the cotangent Laplacian. Okay, so we finally, an hour later, defined the object that we want to use. That leaves us about a half an hour, well, 45 minutes to talk about why we might want to use these objects in practice. And so we'll highlight a couple useful properties of the Laplacian operator. Hopefully now you're hearing me use the word operator, but if you're not used to this kind of theory, you're just substituting the word matrix in your head, and I've convinced you that it's nothing more than a matrix. If I have, n data points, then it's an n by n matrix that I can construct out of those data points. And it's just, you just put in a kernel, by the way, in the data that I have. Okay, so the first thing we'll do is we'll highlight a few of the useful properties we've already seen. Then we'll talk about some nice applications in graphics and shape analysis. And the reason for that, I know that we're at the machine learning summer school, but the reason to look at some of these is that you can see it. These are two-dimensional shapes and you can just visualize what these applications look like. And then we'll talk about applications of machine learning, which are going to use identical formulas, but of course, in a high-dimensional data manifold, you can no longer visualize what's going on. So let's talk about some useful properties. One thing to notice is that, of course, all the Laplacian operator is doing, I think it's most obvious in the formula we had on a graph, is taking values per vertex of a graph and comparing them to their neighbors. Right? And this is a very useful object to use. So for instance, maybe I have a social network and I make an assumption that, which unfortunately apparently is roughly true in a lot of scenarios, I tend to have friends with a similar income to me. Right? And so maybe I have a few people whose income I know. I go on Glassdoor.com or whatever, and I want to infer the income of all the other people in my social network. Then using a Laplacian to propagate that information around is a reasonable, not perfect model for doing so. There's probably less controversial examples there. Laplacians can also be used to measure smoothness, right? We talked about the Dirichlet energy. They're useful for talking about vibration modes. And then one additional property of the Laplacian that's worth mentioning just to connect to the last 2 days of our lectures. Remember, an isometric deformation is something that preserves distances. A different way to state that in 2 dimensions is it's like deforming a domain where you bend it but you don't stretch it. So like a sheet of paper and like origami deforms this way. Elastic stuff does not. Humans approximately deform isometrically because we're full of bones. So this is useful in computer vision. In fact, many algorithms, largely proposed by my colleague in the back of the room, use this as a starting point. One thing that you can check is that the Laplacian operator is in isometry invariant. If I take a manifold and I deform it while preserving the distances, the operator doesn't change, which means that if I build pipelines using the information I get from this thing, then it's invariant to certain species of deformation, or a different way of putting that is that it's intrinsic, which we tend to like in geometry. So anyway, there's many different reasons to study Laplacian, right? I mean, it encodes intrinsic geometry. I shouldn't use the word encodes here because I guess you can't hear the shape of a drum, but it encodes a lot of intrinsic information. It's multi-scale, right? Like some frequencies are very wide and stretch along my domain. Other vibrations are very localized. It has a way of sensing geometry, which is a very annoying research area, using machinery from linear algebra, which we're pretty good at. So it's one way to take a hard area and convert it to something kind of easy. And there's some nice physical intuition which can help us think about these problems. Okay, so let's see some applications in shape analysis. So a very typical task in shape retrieval, computer vision, and so on, is I have a 3D shape, and I have a big database of 3D models, and I'm trying to find other 3D models that are similar to the shape that I have. There's a problem, which is that, unlike data points, shapes are not vectors, so I can't just like search for nearby vectors. That doesn't make any sense, right? Different meshes have different numbers of vertices, and so on. So a very typical thing is to take a surface and map it to a descriptor or a feature, and then search my database for that feature instead. And it turns out that the Laplacian gives some very nice features with some really nice properties that somehow they tell you something about local and global geometry. So for instance, there's 2 slightly different tasks. One would be shape retrieval, right? So that would be like I have a bunny and I want to find other bunnies. The other would be correspondence, which would be I have a bunny and I have a second bunny and I want to find the individual points on those 2 surfaces that relate to one another. And so for that second task, of course, you want to distinguish the points from each other when you have features. Right? Like the feature 0 wouldn't be terribly useful. But at the same time, you want to be stable to certain deformations and maybe intrinsic if you care about that sort of thing. So remember we had this nice connection to physics. One kind of interesting intrinsic observation is that the patterns by which heat diffuses along a surface actually don't change if you bend it without stretching. This is a kind of a difficult experiment to carry out, but if you have a piece of tinfoil and you kind of bend it and you propagate heat, you'll see that the pattern it makes is the same. If you have an infrared goggles, maybe you can see that. But in any event, this sort of inspired an entire series of research papers in the geometry world that said if I want to do shape retrieval, I want to do correspondence, one thing I can do is use patterns of diffusion and vibration to identify points from one another. So one of the early examples was something called the global point signature, which is largely, I think at this point, just historical, but essentially it's nothing more than just the list of eigenfunction values. So I compute the Laplacian, I compute its eigenvectors, and then I describe a point on a surface as just the value of the different eigenvectors. This turns out not to be a great descriptor because the sign of the eigenvector is ambiguous, sometimes they can switch order and so on. So a more stable thing, and one that's used broadly, extremely broadly in the 3D vision and 3D geometry world is something called the heat kernel signature. So in the heat kernel signature, to describe a point, what I do is I put a little delta of heat at that point, and I let it diffuse out as a function of time. Right? So initially 100% of the heat is at one location, and then over time it diffuses along the surface. And it turns out that the diffusion of heat actually encodes the curvature of a surface. And this makes sense. So like if I'm carrying around this cup of tea, but I'm not drinking it. If I put a little bit of heat right on the tip of my finger and let it diffuse outward, it has nowhere to go. Right? You see that? It diffuses around the outside and it just goes back. And so the rate of diffusion here is relatively low. On other parts of the surface, maybe places that are less curved, when I put the heat, it just diffuses outward and it never comes back. So the heat kernel signature is a way to describe a point on a surface where what you do is you put a unit of heat at that point, and then you just sit at that point and you measure how much heat is left as a function of time. And that is a function over time per point on the surface. It turns out to be an extremely effective way to distinguish points from one another on a domain. And so this is plotted here for a 3D model, so you can see the numbers correspond to the different points. So 1 and 2 are the front paws of the dragon, hands? I don't know, the front feet of the front part of the dragon is number 1 and 2, the back part is 3 and 4. And notice when we plot the heat kernel signature, they very cleanly distinguish between those two things. Notice there's also a challenge here, which is that the two sides of the dragon are indistinguishable because there's a symmetry. This work has been extended in about 5 billion different ways. One of the simple ones is to replace the heat equation with the wave equation. That leads to something called the wave kernel signature, which turns out to empirically be more effective for a lot of shape retrieval tasks. I think there's a lot of mythology as to why. So if you have a good mathematical explanation, I'd be curious to hear it. And there's many others. So and so this falls in the category of what we call spectral descriptors of points on surfaces. And it's sort of one of the bread and butter techniques in the geometry world for solving these tasks in vision, like shape retrieval, mapping, and so on. In fact, of course, Lippmann and Bronstein, you might recognize one of the authors, even proposed maybe learning a spectral descriptor based on the eigenfunctions and eigenvalues of the operator. So this is one thread in the geometry world, and it turns out that Laplacian operators appear everywhere in shape analysis and machine learning. In fact, sometimes they appear by accident, like it'll appear in an algorithm and people don't call it out for what it is. And so I thought we'd have a quick grab bag of some other places. So another sort of a place where Laplace operators appears is computing distances between points, for instance, harmonic or biharmonic distances. So let's say that I have a manifold, and I want some notion of distance, but not necessarily geodesic. It turns out that geodesic distances can have a lot of problems. So for instance, in 3D models, maybe I want the distance from one hand to another, right? So the typical distance would be like that as a path. But then I have an annoying data set, and in one of my models, they clasp their hands together. Then what happens to the geodesic distance between the two sides? Well, suddenly it's close to 0. And so it turns out that basically for that reason, geodesic distances, like shortest paths on a manifold, are often quite unstable. Or like in this high-dimensional setting, if I start introducing a few extra points, then the geodesic distance can change quite a bit. For a lot of applications, I do want to measure similarity of my data points. In this case, just proximity of points on the surface. But I'd like it to be stable to small changes, and that led to a whole series of what people call spectral distances, so biharmonic distance, diffusion distance, and so on. And essentially what you do here is you put a little pinprick of heat. It's the same analogy we've already had. You diffuse it for some fixed period of time. And now, to compute the distance between 2 points, you compute the distance between those heat functions over the entire manifold. So you like just, so for instance, in one dimension, heat diffusion is the Gaussian distribution. It's a bell curve. So this would be like measuring the distance between 2 points on a line by taking 2 bell curves, subtracting them from one another, and integrating. It turns out this is stable to many species of noise, which is pretty nice. Yes?
What if you change topology a bit? So in that case, also the signatures would be similar, right? All the points that were one of the shapes there are right, but then when you change topology, should it also be stable to that?
Sure. So the question, for those of you who didn't hear, was like, why wouldn't these things be sensitive to changes in topology as well, right? Like this example where I join my hands together and suddenly the shortest path changes. And they are, and globally speaking, like obviously something changes. But for instance, think about diffusion. So let's say that I have a very small diffusion time. And I want to know the distance between my knuckle, my other knuckle. But the diffusion radius is like something like the size of my hand. Then when I join my hands together, the distance actually doesn't change that much because in the time that I've allotted, not very much heat diffuses from one side to the other. So there's a parameter there, right, which is diffusion time, which is a little bit tricky to choose, but there is a level of stability that you can achieve. So if you know the scale where your error tends to appear, then you can incorporate that in the distance that you choose. It's a great question. It does turn out that the Laplacian operator, oops, did I hear a question? No problem.
Okay. I had a question back to the heat kernel thing, which might be related, I'm sure. Did it matter at all where you put the initial delta of heat? Or
It matters 100%. That's the place, the point that you care about.
for the final
Oh, yeah. So this is, for the heat kernel signature, the task is slightly different. It's to describe the role of one point on a surface. And so what you do is you put the pinprick of heat at a point, and then you only measure the heat diffusion at that point. This is called the auto diffusion function. So I just ignore all the other points. A different way of putting that, if you're a PDE person, is this the diagonal of the heat kernel. There's a different technique out there called the heat kernel map, which does the opposite of that, where you have like fixed landmark points, and you measure diffusion from those. But then you need to know the landmarks. Yeah. One kind of surprising fact is that the Laplace operator actually encodes geodesic distances, so if you care about those, you can find them. This is a famous result in mathematics. It's called Varidan's theorem. So essentially what it says is if you take the heat kernel and you take its log, you take the square root of the log of the heat kernel. Remember, the heat kernel is the thing that tells you how much heat diffuses from A to B, where A and B are points, in some time t. When you take t to 0, that value is actually geodesic distance. This sounds crazy, like you look at this formula, it's not totally clear why. But remember that the heat kernel in Euclidean space is just Gaussian distribution. It's just like e to the minus distance from x to y squared. So if I wanted the distance from x to y, how could I get it? Well, I could take minus log of e to the minus x minus y squared, take the square root of that, and what I got was distance, right? So in Euclidean space, it's equal, right? This is an equality relationship. It turns out that on a curved domain, it's only approximate, but if you take the limit as t goes to 0, that number converges to distance. And so that led, for example, my colleague Keating Crane to define a very popular technique for computing geodesic distances on a surface, which turns out to be kind of a tricky task, by using this formula. So he simulates heat diffusion and then just takes the log, and this is a good approximation of the shortest path between 2 points on a domain. Incidentally, this carries through in spectral graph theory as well. So if you want a really bad algorithm for computing the shortest path between 2 vertices of a graph, one way that you can do it is to solve the heat equation on the graph and take the log, and you'll see that you actually do get the distance back. Okay, another place where this appears in the computer graphics world is something called parameterization. And here, our goal is to take our 3D cat and map it into the plane. So computer graphics people care about that because maybe I want to put a texture on the cat, but I'd like to store it in a JPEG image, right? So I have to map the thing into the plane, store the image there. That's called a texture map, unsurprisingly. And then use the colors from the image on the 3D shape. Does this task remind you guys of anything that we've already talked about? This is exactly like an embedding problem, which we talked about 2 days ago. And we're going to see that you can embed data from the Laplace operator using exactly the same machinery that people in computer graphics are using to embed surfaces for texturing. Namely, we're going to compute the Laplace operator, use its eigenfunctions, or solve a linear system to map it into a lower dimensional domain. Maybe not 2 dimensions anymore, but something higher. So again, our goal here is just to use these graphics applications as a way to visualize all the cool things that this one matrix is allowing us to do. Okay, so finally, we can talk about some applications in machine learning of the machinery that we've built up. Right, so what is our story so far? We have an operator, and again, an operator is just fancy word for a matrix. And in fact, the matrix is pretty darn straightforward, right? It's nothing more than maybe sorry, I'm like gonna spill this tea by the time I'm done talking. Maybe the matrix is roughly just a Gaussian in every pair of points, the distance between every pair, with a little bit of an edit down the diagonal. And that matrix encodes all kinds of beautiful stuff, right? It tells you how to diffuse information around on your manifold. It tells you something about vibration modes. It tells you something about how to identify one point from another. Right? These are all things that we've seen so far. So here's going to be the nice thing about the machine learning algorithms that we talk about, is we've already seen them, right? So for instance, if I want to measure how similar 2 points are in a data set in an intrinsic fashion, so in a way that's sensitive to the manifold that my data lives on, how could I do it? Well, I already gave you a formula for the Laplacian of my data set, approximately, right? Remember, I put it in a Gaussian and then I edit the diagonal. Well, now I can solve diffusion equation on this high-dimensional data manifold. I might not be able to render it anymore. I can't look at it, but algebraically, it's exactly the same. And now, if I want the similarity between 2 points, I can use diffusion distance formula. This is nothing more, than the L2 distance between these diffused point kernels. And out comes a measure of similarity of data points. And roughly, the really nice thing about being in a research area like spectral geometry is that you get kind of a 2-for-1 when it comes to publishing research papers. You can write one paper in the low-dimensional computer graphics world and then secretly write another one in machine learning, but really they're all the same code. And nobody will ever know. So it's great as a person in academia working in this area because exactly the intuition in the low-dimensional case can carry through to higher dimensional area. So one very well-known example of this is in semi-supervised learning. For those of you who aren't familiar with the terminology here, semi-supervised learning is this scenario where oftentimes it's very easy to collect unlabeled data. So for instance, let's say I'm talking about labeling photographs, right? It's very easy to go on, Google Images, whatever, and download billions and billions of photographs. The only problem is that I can't say anything about those photographs. I just know they're big collections of pixels. So it's very easy to collect unlabeled data and much harder to collect labeled data, like an image plus a word describing what that image is, right? That's much less common. And so in the semi-supervised regime, the question is, if I have all this unlabeled data around, can I use that to improve the inference that I'm able to do from the sparse set of labeled information that I have? Does that make sense? So these are obviously very manufactured examples. But here's kind of a funny one. I think on the right-hand side, it's clear what's going on. So let's say that my data set, for whatever reason, is comprises of 2 different curves that kind of intertwine with each other. Again, this is totally manufactured example. It's just to illustrate why these tools might be useful. And actually, the task that I'm trying to solve is to distinguish one of these curves from the other, right? But unfortunately for me, somebody's only labeled a few data points on these two curves. Now, if I apply, what are our favorite machine learning on kind of low-dimensional data? Like, I apply SVM to this data. What's going to happen? Well, I'm trying to find a hyperplane that cuts through it. Obviously, I'm not going to do a very good job because these things are tangled up with each other. This is a great example where maybe these manifold learning tools are useful, right? Because hiding inside of my three-dimensional data set are two one-dimensional manifolds. It's a really complicated way of saying two curves. Okay? So in the Laplacian-based semi-supervised learning, what do? Well, you compute the Laplace operator of your data set. In this case, it's all of the points on these two curves. So remember, we have many points on the two curves, but only a few of them are labeled red or blue. And think about what that Laplace operator is going to look like as a matrix. Let's say that I take the rows and the columns and I sort them. I put all of the red ones first and then all the blue ones. Obviously, I don't know which ones are red and blue, but maybe I just for argument purposes I did. Then what's going to happen in the off-diagonal blocks? So in other words, the block of the matrix which corresponds to the relationships between the red points and the blue points. Well, they're pretty far apart from one another, right? The distance, just these two curves are separated by some positive distance. Remember that the Laplace operator is like a Gaussian in distance, so it decays very quickly as 2 points become farther apart. So roughly, what is that matrix on those two pieces? How many of us vote non-zero? How many of us vote 0? How many of us are just not going to vote? We're tired. We want to go home. Haven't had enough coffee. Yeah, no. The Laplace matrix is going to be basically two blocks with no connection in between them, because between them is a Gaussian in a very large distance, which is essentially 0. And so if I use that to diffuse information from the labeled points to the unlabeled points, what I'm going to get is the information diffuses along the spiral instead of in 3D, which is what I want. Yeah? And so this, Laplacian-based semi-supervised learning, has been proposed many times and in many places. This paper in 2003, I think, is one of the earlier references. Proposes solving the following optimization problem. Here, maybe I have a real valued label for my data. So that's going to be the label as F here. So F is prescribed at a few places. This is where I have a label. And now, what I'm going to do, Wij is a Gaussian in distance, so the farther apart data point I and data point J are, the smaller W is. And I'm going to solve the optimization problem on the screen, where F of K is fixed at a few sparse points, and then what I want is that nearby points get nearby labels. So does optimization make some sense? What does that objective function remind you guys of? This is exactly the Dirichlet energy. Yeah? And so really what's going on here is they're solving a diffusion problem. I have a few labeled points, and I'm trying to diffuse the labels from those points to the rest of the data set using a Laplace operator, which is encoded in this matrix W. So as like kind of a nice example, here they've constructed a kind of two rectangles connected by a line. If I didn't use the Laplace operator, then maybe the red point would have information diffuse to the blue points right underneath it, because like on the two-dimensional plane, they're pretty close by. But using this intrinsic technique, there's this bottleneck in the middle that the information has to flow through. Okay. There's many different techniques that kind of look like this one, and essentially they all have very similar spirit, right? You have your data set, you construct the Laplacian, you have a few labeled points, and you want to diffuse information from those to the rest. Another one, which I think actually predates this a tiny, tiny bit. Yep, by 1 year. Builds up a Laplacian, yes?
Computing it feels like it should be other ways of computing classical diagonal structures, and look at that as a structure too.
That's a great question. So to repeat the question here, it was, aren't there easier ways for detecting block diagonal structure? The answer is absolutely yes. I mean, there's nothing, this particular Gaussian formula that we have for Laplace operator, maybe in this case isn't so sensible. So like Caritas neighbor graph will give you a reasonable graph on your data. The question is, how do you use that, right? So after you have those block diagonals, you still have to decide how you diffuse information around in your domain. So yeah, maybe you can separate it into two pieces, but maybe the labels in the individual pieces don't quite agree, and this machinery still applies. But related to that, so the other half of our colleague question here was, can you use eigenvectors to detect that block diagonal structure? The answer is absolutely yes. And in fact, if you look at this related technique, that is precisely what they're doing. In this earlier work, which is, they even call it using manifold structure for partially labeled classification. This is a very long sentence for semi-supervised learning. Essentially, what they do is, rather than using diffusion equation, they use the eigenvectors of the Laplacian to move information around. The advantage here being that you can solve your problem in a kind of a smaller, low-dimensional subspace rather than solving a giant matrix. But remember that I told you that using Laplacians to spread information around can be a little bit dangerous. And in fact, all of these methods are subject to a mathematical phenomenon known as loss of ellipticity. So those of you with a mathematical background might recognize that the Laplace equation is a very famous example of something called an elliptic PDE, which is like the PDE version of positive definite matrix. And there's something really funny that happens in the Laplace equation, which is it is elliptic, except right at the points where you've prescribed information. Right? And so what tends to happen is that these techniques can often over-smooth data unless you're quite careful about how you use them. Yeah. Okay, but in any event, there are many different techniques that use the same kind of intuition to build up different algorithms in machine learning that want to take advantage of the data manifold. Another big class of algorithms out there is something called manifold regularization, where the basic idea is that I have some machine learning problem, you know, that's maybe supervised, right? That's this first term, this loss function that I've shown you in the slide. And I'd like to regularize it. Right? And remember that regularization, just as a general term, is like I have an optimization problem for a machine learning problem, and then I add a second energy into my optimization problem to somehow make it behave better or generalize more. And so the idea of manifold regularization specifically is that I want to design a regularizer for machine learning that leverages the nice manifold structure that I have in my unlabeled data. I know that's a mouthful. So as a simple example, let's say that I'm talking about regression problem. Right? So remember, a regression problem is like I have a few data points. It's like a function f of x, and I want to impute the values of f of x at x's that I haven't seen yet. And so what are the typical things that you want in regression for for example, in non-parametric regression? Well, for one, I'd like it to match my data, right? So like at the points where I have information, I'd like it to agree. That would be a very easy thing to encapsulate in a loss function. But then the other thing that we talk about when we talk about regression problems is that I want the regressed function not to be too complicated, right? To be fairly smooth. Right? So for instance, when people talk about polynomial regression, you often run into trouble, right? Because if I have a very high degree polynomial that goes through data points, they have ringing and all these other crazy artifacts. And so a very typical thing to do in a regression problem is to have the sum of two terms, right? One term is how well does my regressor fit my data, and then the second term is how smooth is my regressor. So what do you think we do in manifold regularized regression? Well, maybe I have a big unsupervised data set, which is sort of roughly the support that I care about where my regressor is going to be used. So rather than just evaluating its smoothness generically, maybe I only care about the smoothness on my data manifold. So I approximate the Dirichlet energy and I use it as a regularizer for my machine learning task. And it turns out there are many contexts where this is useful. So if you take a look at this information, then there's these techniques rather. There's manifold regularized least squares. There's manifold regularized support vector machines. Essentially, any one of these tools is very simple. You take your favorite optimization problem for solving a supervised machine learning problem, and now you have this big unsupervised data set. So you just add another term onto your optimization problem that evaluates the smoothness on the unsupervised data using a Laplacian like we've already talked about. So I'll refer you to this research paper for the details, but I think you're now equipped to read these things without too much excruciating pain here. Okay, finally, we should mention a very famous piece of work in the applied math literature. This is something called diffusion maps. And diffusion maps are a technique for embedding. We'll kind of go full circle for my 3 lectures at MLSS here. And this is one of the most popular techniques out there for embedding data because essentially it's one of very few methods out there where you can say something theoretical about it. And the basic idea here, just like we've already talked about for that E-kernel signature, and roughly this is just a high-dimensional analog of that modulo some cosmetic changes to the formula, is that I'm going to use the Laplacian eigenvalues as an embedding of my data. So let's unpack that a little bit. So I have a big cloud of data points, and maybe the embedding of my data is actually not so useful. So for instance, let's say I have a big data set of photographs. And photographs are really complicated data points, right? They're just long lists of pixel colors. But is the distance between photographs and in R to the rows by columns space, is that a particularly meaningful distance? No, right? Like it doesn't capture similarity or any of this other stuff, right? So maybe I construct, some notion of similarity between the images. I use that to construct a Laplace operator. And now I compute the eigenfunctions of that operator. There's nothing more than eigenvectors of a matrix. But eigenfunctions of operator sounds way cooler. Yeah? And what is that? Well, a single eigenfunction is one number per data point. Right? So like one number per image, maybe. So if I compute 10 eigenvectors, then in effect I have a 10-dimensional descriptor for every one of my data points that knows something about the intrinsic structure of my data set. And so in the diffusion maps algorithm, what do? Well, I have some distance metric, right? Something I want to embed. I construct this Laplace operator. I've already given you a formula for that, right? You just take e to the minus distance squared, scaled by some value. I compute the eigenvectors of that matrix. And if I want a k-dimensional embedding, I compute k eigenvectors. And now every data point is associated to a list of k numbers. And that's exactly my embedding. Notice that relative to the algorithms that we talked about on Monday, this is no harder to implement. Like when we talked about MDS, we took eigenfunctions of the pairwise distance matrix, squared, I guess. Now we're just taking e to the minus pairwise distance matrix and taking eigenfunctions of that, but the interpretation completely changes. Rather than embedding based on Euclidean structure, we're now embedding based on the way information diffuses around. And so I encourage you to take a look at the diffusion maps research paper and the huge body of work that has come after it, because it's a really beautiful example of one technique for embedding that has really nice theoretical guarantee and understanding when it comes to like your data set being sampled and the convergence as the number of data points increases, how to choose the variance of your Gaussian, which is a little bit of a tricky parameter when it comes to these techniques and so on. So with that, I think we've reached the end of our treatment. I know this is a bit of a mathematically complicated topic. We still have about 10 minutes. Are there any questions that I can answer regarding either this technique or the two areas that we've talked about in the last 2 days? Don't all speak at once now. Yes? How to choose the metric for building your K and N graph? I wish I had an answer. You're 100% right. Sure. So let me repeat the question so that everybody can hear. So the question was, how do I actually know the right way to choose, for example, a K and N graph if I want to use that particular formula for a Laplace operator? Because obviously, my K nearest neighbors in different spaces could be quite different, and this will really strongly affect the behavior of the algorithms I've talked about today. And your colleague here is absolutely right. This is one of the most tricky sort of parameters and things to get correct. And in some sense, it's a chicken and egg problem, right? If I had the perfect embedding of my data, I probably wouldn't need all of these techniques. But at the same time, to get that nice embedding, I'm using these algorithms that depend on having a good embedding. So what's that about? And to some extent, I don't have a great answer for you. One thing that I can tell you is that it's oftentimes much easier to get very rough relationships, like these points are close to each other and these points are far, than it is to have a reliable metric. So let me repeat that. So like, let's say that I have a bunch of data that's embedded in 3D, like this twisted together curved example. The metric in 3D here is not reliable, like we talked about, right? Like this is not a useful metric. But computing the k-nearest neighbors for small k in this metric is actually a reasonable way to extract things that are similar. And so one of the really beautiful things about Laplacian-based techniques is that I don't need a full distance metric to have a reliable Laplacian. The only thing that I need is a reliable technique for identifying the nearby data points, which is often a much easier task. Is that true universally? No. Yeah, but even mathematically this is backed up, right? Because if I make small deformation of a geometric domain, the nearest neighbors don't tend to change very much. I see you have another question here. That's absolutely right. Right. So you're saying that maybe somehow by using Euclidean metric, you're destroying the nice manifold structure. For a little bit of perspective on these sorts of questions, the places that I would look are in Misha Belkin's work and some of his colleagues on this particular Laplace operator, which is the one that I think you're asking about. I think for k-nearest neighbors it's a little bit brittle because there's a binary decision, am I your neighbor or not? This one's a little bit easier to analyze. And what they show is that at least if the points are densely sampled and I choose this t parameter carefully, notice those are two very big ifs. But under those assumptions, one thing you can show is that actually the operator that you get here is a reasonable approximation and conversion of approximation of the Laplacian of the manifold, not of the extrinsic space. So this is an example where even though I'm computing Gaussians in 3D, what I'm actually getting is the two-dimensional Laplace operator. However, doing that in a controllable fashion is quite difficult. So in practice, what do people do? Oftentimes they try a million different t values until they get the behavior they expect. Is that scientifically great? No. But in some sense in machine learning, maybe we call that a meta-parameter and we move on. But that's where theory meets practice. And I think there's many, many questions hiding here that are really non-trivial and interesting to study. There's a question here. Mm-hmm. Connections is exactly the right word, but maybe I'll differ on that. Yeah, so the question was, somehow we've seen many different notions of smoothness, right? Certainly in an RKHS, you have some notion of smoothness hiding there. Optimal transport smoothness is actually a little bit tricky. So regularity theory for optimal transport is a relatively recent development and quite hard to theorize about. Optimal transport maps can be discontinuous. So maybe we'll differ on that, although I'm happy to tell you about the theory. There's some cool stuff there. You should search for Caffarelli's theorem, I think is one. But in any event, one thing you should notice, look at this matrix W. This is a kernel. This is the Gaussian kernel evaluated pairwise between points. So there's no mistake that these things are related. And in fact, I think, although you shouldn't quote me on this, I think if you take the Gaussian kernel and you replace it with any kernel that decays sufficiently fast in distance, probably it doesn't affect the convergence of this operator a whole lot. But I could be wrong about that. So that's something I would have to look up. So these things are definitely closely related, and I think actually oftentimes they're justified by very similar theoretical ideas. That's kind of one of the very cool things about this area is that oftentimes many people end up converging on the same idea from very different perspectives, right? Optimal transport is another great example of that, right? And that's why the optimal transport problem has like about 10 different names, right? There's optimal transport, Cantorvich distance, Wasserstein distance, Mallow's distance, Earth mover's distance. They're all the same thing, often named after the guy that thought they thought of it, because somehow these are very natural ideas and they appear in many different places. All right, are there any other questions? Yes, back here.
So, to
Yes.
without them. And for the graphs, there is not such thing as boundary conditions, just topology defines it, or like, what's the connection?
Mm-hmm. Oh, okay, just a comment on that. Yes, my answer is yes. Right, so to repeat the question, I did a bit of a sleight of hand. I was a little sloppy in the way that I talked. That when we talked about the problem of can you hear the shape of a drum, there were boundary conditions. In fact, they're called Dirichlet boundary condition. And what that means is that we took the side of the drum and we glued it down, right? When the drum vibrated, the sides of the drum were remaining still. But somehow when I talked about these algorithms here, we didn't talk about boundary condition at all. There's a reason for that, which is that people in machine learning tend to be quite sloppy about this sort of thing. But that's actually okay. And let me give you a few reasons why it's okay, and then a few reasons why it's immoral and you should never do this. So I'll give you both sides. So on one side, depending on how familiar you are with the theory of partial differential equation, there's sort of two ways to understand boundary condition. The undergraduate version is that you have what we call a strong form PDE, meaning it's like the relationship between derivatives of a function, and you explicitly write down your boundary condition. And then another is something called a weak form or variational form for PDE, which is to notice that many differential equations actually are solving optimization problems. We actually saw that here, right? Laplace's equation comes from minimizing Dirichlet energy. So it turns out that there's a really interesting phenomenon in the theory of PDE, which is that oftentimes if you look at the variational form of a PDE, you don't need boundary conditions, but they arise naturally when you take the derivative and set it equal to 0. So for instance, if you take an undergraduate PDE course, you'll learn that the wave equation has two different boundary conditions. Right? One is Dirichlet, meaning that you fix the boundary